Okay, let's talk a little bit more about divisibility. So, last time we have seen before things like if you have two coprime numbers. So, suppose let A, P, P coprime, then the most important property that we proved about them is that you can find integers m and n such that m a plus n b equals 1, okay. And this was really our trying to understand how to pay various sums of money if you only had a 10 rupee coin and a 17 rupee coin, for example. So, these are the two numbers a and b are 10 and 17, and the various sums of money that you can either pay or receive are all of this form. You take m coins of 10 rupees and n coins of 17 rupees, then you have ma plus nb, and you can also receive coins. So, then we sort of had this entire analysis which said we can get 1 by just using certain number of coins of 10 and 17, and this was the general fact if it is coprime. Now, as a consequence of this, we also said not just 1, even if I had to pay any sum of money whatsoever. So, this is statement 1, but as a simple consequence we also saw that let p be any integer, okay, and a, b, b coprime as before. So, a and b coprime as before, then you can do the same thing. You can find two integers, it is called m and n again, such that ma plus nb equals p. Okay, and this was simple. If you knew how to do this one, you just multiplied both sides of this equation by p and you would be able to find a solution to the equation below. Okay, so all this is under the assumption that a and b are coprime integers, but if they weren't, for example, if you had the numbers 10 and 16, then we also said this, that if you try to write numbers of the form 10m plus 16n, then you certainly can't get 1 in this manner. You can definitely not find m and n such that 10m plus 16n is 1, because for sure the left hand side is an even number, both 10 and 16 are even, and therefore whatever you can get will have to be an even number. So, here is the question, can you find m and n such that 10m plus 16n is 2? Okay, so that is the smallest even number, and let us see if we can solve this equation. Okay, so to try and do this, so the question is this, find m and n integers such that this happens. Okay, and let us do the following. So, there is of course a 2 common factor on both sides. So, we will cancel the 2 from both sides of the equation, rewrite it as 5m plus 8n equals 1, and now you observe that this is actually like our previous situation. Instead of 10 and 16, the two numbers we are dealing with are now 5 and 8, which happen to be coprime, right. So, remember 5 and 8 are of course coprime integers, which means we can certainly find m and n such that 5m plus 8n is 1. Okay. What are those? For instance, we could look at 5 times minus 3 is 15 plus 16, which is 1. Okay. So, you can take m to be minus 3 and n to be 2, and you would have solved the equation 5m plus 8n is 1. Now, having solved that equation, we just go back, we just multiply this equation by a 2 and you would just get a solution to the previous equation. So, 10 into minus 3 plus 16 into 2 is just going to give me the answer to the original equation. Okay. So, we can definitely get 2 as this sort of combination 10m plus 16n. But what about other pairs of numbers? So, here is a similar question. Instead of 10 and 16, if I took 12 and 16, so if a is 12, b is 16, and then I want to do the same thing, I want to find integers m and n such that 12m plus 16n equals, well, what can I do? Again, the left hand side is an even number, and so maybe I can ask, is it possible to somehow get the number 2 by this sort of linear combination? Okay, so let us try the same trick that we did in the previous problem. We will cancel the 2 from both sides of the equation. So this becomes 6m, 8n, and the left hand side is a 1. Okay, but now we already see that we are in trouble because the two numbers here are 6 and 8, and 6 and 8 are not coprime integers. 6 and 8, well, again both are even numbers. So we already know that we cannot get 6m plus 8n to equal 1 because you can only get even numbers this way, you can't get odd numbers. Okay, so it's clear that this is however not possible. So I cannot get 2 in this way. I cannot find m and n for which 12m plus 16n is 2, but what I can do is the following. Let me change the question a little bit. Can you find m and n? So here's another question, the next one. Find m and n such that 12m plus 16n is 4. Okay, so observe 12 and 16 to start with, they are even numbers all right, but in fact they are a little more than that. They are both divisible by 4. Okay, so the left hand side is always going to be a multiple of 4 in fact, not just a multiple of 2. Okay, so now let us see if we can somehow get 4 in this way. So to solve this equation, we divide both sides by a 4, and now this becomes 3, this becomes 4, and this becomes a 1. Okay, now the question is, can we solve this equation? And this we can do because the 3 and the 4 are now coprime integers. So observe that the 3 and the 4 here are coprime. Therefore, I can solve this equation 3m plus 4n is 1, right? That is the main property of coprime integers. For example, let us see what is the simplest solution we can give here. We can look at 3 into 1 or 3 into minus 1 is 3, 4 into 1 is 4, so 4 minus 3 is a 1. So 1 and minus 1 are the solutions here. Now having found these solutions, all we have to do to solve the original equation is to just multiply both sides by a 4. So I multiply both sides by 4, I get 12, 16 times 1 is a 4. So my solution remains the same, m equals minus 1 and n equals 1. Okay, so this is sort of the situation for pairs of integers a and b which are not necessarily coprime. Okay, so the question now is the following: what's, how did I get this number 4 here? What is this 4 got to do with the original numbers 12 and 16? The answer is that 4 is in fact a divisor of both those numbers, but it is in fact the largest possible divisor of those numbers. Okay, so recall we already had a 2 as well, so that was our original attempt. We looked at 12m plus 16n and we tried to see if we could get that to equal 2. Okay, so this number 2 is also a divisor of both 12 and 16, but it is not the largest common divisor. Okay, so let us see what are the common divisors. So we already talked about common divisors or common factors in this case. So if I take the numbers 12 and 16 and try to write out its common factors. So let us see what are the factors of these numbers. So for 12 I have got, so I will also write the negative factors 1, 2, 3, 4, 6 and 12, and for 16 I have got 1, 2, 4, 8 and 16, and among these possible factors, if you sort of look for the largest guy, you will see that it is the factor plus 4. So the largest common factor or the greatest common divisor, as it is sometimes called, so greatest common divisor or largest factor. So this is often abbreviated to GCD of the numbers 12 and 16 is this number 4, which is just the largest among the common divisors. So what are the common divisors? So you will see that these are the common ones, 1, 2 and 4. Okay, of them 4 is the largest. Okay, so that is really the point here. So how did we get this number 4 on the right hand side? What is the thing that you can put on the right hand side in order to find a solution to this equation? Well, it seems to be the greatest of the common divisors. Okay, so let us just make this a little bit more formal. So what is the definition? Given two numbers a and b, a and b be integers and at least one of them non-zero, so we do not want to deal with both of them being 0, then the GCD of a and b is defined to be the largest integer d such that d divides both of them, divides a and d divides b. Okay, so that is just the intuitive or what the English word greatest common divisor English phrase means. Now the key property, and this is the thing that we really used in our earlier example. So let us just do it on the side. If I had 12 and 16, I said the greatest common divisor was a 4. Now what happens if you divide both of them by a 4? That is the thing that went into the previous equation. So this became a 3 and this became a 4. So those were those two coefficients that we got, and they turned out to be coprime. So when you divide by the greatest common divisor, what you are left with is a pair of coprime integers. So that is what we will formulate in this lemma. So if d is the GCD of a and b, then the numbers a divided by d and b divided by d are coprime. Okay, so we see this from this example, but let us just prove this formally. So the proof is easy. So what do we need to prove? We need to show that a by d and b by d do not have any common factors other than plus minus 1. Okay, so let e be a common factor or a common divisor of a by d and b by d. Now what does it mean for it to be a divisor? This means I can write, so there exists a number m, integer m, such that a by d is some multiple of e. Okay, and likewise there is an integer n such that b by d is also some multiple of e. Okay. Now let us just rewrite these equations as a equals m times dE, b equals n times dE. Now what these two equations mean is that the product of d and e divides a as well as b, right. Now what does this mean? This means that dE is a common divisor, d times e is a common factor or a common divisor. Of a and b. Okay. But d was supposed to be the largest or the greatest common divisor, right. So d is the GCD a and b. So what does this mean? This tells you that dE is at most d, right, because d is the largest, and so this means that e is at most 1. Okay. So let us go back. So I should have, well, let me say let me take a natural number e. So I mean there is always, when I have a divisor, I also have a positive and a negative version. So I do not really need to worry about the negatives. So let me, to start out, make the assumption that e is a natural number which is a common divisor of a by d and b by d. Now when I do this, what I have also concluded from this equation is that e is at most 1. So together I conclude that this number e I started out with must have been the number 1. Okay, and that is exactly what I need. This means that a by d and b by d are coprime. So that completes the proof. Now what this lemma allows us to do is to sort of do in general the thing that we did with the example of 12 and 16 for example. So, here is the proposition. Which says that let A and B integers not both 0, then the GCD of those two numbers is the smallest possible number, or is the smallest natural number that can be written as m times A plus n times B for some choice of integers m and n. Okay, and let us prove this. So, we did this by example, so let us do it in general. So, the thing that we already said is this, that any number that is of the form ma plus nb is definitely a divisor. So, let us call the GCD something, let us call the GCD as D. Then observe that D, so we already proved this means D divides A and D divides B in particular, and therefore, this is one of the things we showed already, D divides MA plus NB. So, this is something that is always true. So, what does that mean? That MA plus NB is it is at least D. So, let MA plus NB be a natural number, then that number is a multiple of D. Okay. So, is okay. So, if it is a positive number, if it is a natural number, then it is at least D. So, it can be D, 2D, 3D and so on. Okay. Now, let us look at the other side. So, we want to show that okay, maybe I should also write this. So, it is a multiple of D, therefore, if MA plus NB is a natural number, then it is at least the smallest value it can take is D. Now, the claim is that you can find special values m and n such that MA plus NB is exactly equal to D. Okay. So, let us do that. So, now what we claim is that you can find m and n such that MA plus NB is equal to D. Okay. And how do we prove this claim? We just copy the proof that we did for the example of 12 and 16. So, how do we try to do this? Let us do it again on the side. So, I know that I want this, but I will divide both sides of the equation by D so as to rewrite it in this manner. Okay. But this equation that I get at the end, I know I can solve, because A by D and B by D are now coprime integers. So, we know that these are coprime. So, we can find m and n such that m times this plus n times that is 1. Okay. And then we go back and multiply the equation by D again. So, that is sort of what we did on the margin. So, let us just rewrite the proof sort of in reverse. So, observe that A by D and B by D are coprime. So, that was our earlier lemma. By our earlier lemma, so by what we proved before, there exists integers so that this is true, and now we just multiply the equation by D. So, multiply by D throughout to conclude that MA plus NB equals D. Okay, and that completes the proof. So, that is the end of proof. So, what we have managed to prove, so this is the proposition that if you look at this, the natural numbers which are of this form, which can be written as MA plus NB, then the smallest among them is in fact the natural number B, the natural number D, the GCD of A and B. And in fact, if you look at what are all the natural numbers that you can obtain in this way, that you can obtain, so in fact a little corollary or something that we have seen along the way in the proof is the following. You just look at all numbers which you can get like this. So, consider the set of numbers MA plus NB as M and N vary over all possible integers. This set, every element of this set is in fact a multiple of D, the GCD of A and B, and in fact this set coincides exactly with all multiples of D. So, let me rewrite it like this. So, the right hand side is just the set of all multiples of D. Okay, and D is the GCD of A. Okay, and this is really the problem that we started out with, which is trying to see which are all the sums of money you can pay if you only had coins of denomination A and B. So, the final answer says this: if I only had a coin of denomination A rupees and a coin B rupees, then using only these two coins, the sums of money you can pay are exactly multiples of the GCD of those two numbers. Okay, and every such multiple you can pay just using these two coins. So, that is the connection to all the things we have been doing before. Okay, and the proof of this is just just leave this as an exercise for you guys to try your hand out. So, it's more or less the things that we did along the way in the proof. And here is the interesting sort of an interesting thought, if you will. What we have done is really given two different ways of thinking about what the GCD is. So, on the one hand, if I have the numbers A and B, we have said the GCD is sort of the greatest. So, there is one point of view which thinks of it as the greatest among things which divide A and B, right. So, this is the greatest common divisor, whereas this proposition here, which is this guy, says the GCD is actually the smallest natural number that has some other property. Okay. So, on the one hand you have a way of thinking about D as the greatest among natural numbers which have a certain property that they divide both A and B. On the other hand, you have got this other way of thinking about it, which is to say you take all possible numbers of the form MA plus NB, and among all such numbers, so that is an infinite list of numbers of the form MA plus NB, I look at the natural numbers, among all of them the smallest natural number that I can find. So, it is the smallest natural number of the form MA plus NB. So, there are two descriptions, one as the greatest and another as the smallest.